Hey, this is Brock Lemiers, and in this video I'm going to continue talking about AC signals, and I'm going to specifically introduce the electrical power grid and discuss how AC signals are used to distribute power across our nation and how we use transformers to step up and step down the voltages that are delivered to households in order to overcome loss in the transmission lines. Okay, so the electrical power grid, here it is, the grid. So when we talk about the electrical power grid, it is this interconnected network of wires that transmit electricity from generation plants to the end user, to our homes or to plants that need electricity. And it's actually, it's evolved over time, right? We started kind of on the East Coast generating electricity, and you can kind of see that it tends to follow population. It also tends to follow areas where there's a lot of generation. So if you look at Texas, there's a lot of oil down there, and so they can create a lot of electricity. And then you can see, at night you can kind of see where all the high density population areas are in our country. And so out in the Midwest, in the Rocky Mountain region, there's not a lot of people compared to on the East Coast where it's highly densely populated. So you have a lot more electricity use out there. And the power grid has actually evolved over time, and it started off with these little kind of sections that were called interconnections. And nowadays, it's starting to be somewhat continuous, but we still have these things called interconnections. So you got like Western and Texas and Eastern, and these represent kind of grids where if the Western interconnect went down, then the Texas and the Eastern wouldn't go down. And the advantage of interconnecting everything is so that if you did have a fault or something went wrong in one area, like a generation plant went down, let's say in Montana, then we could use some of the electricity from the rest of the country, and we wouldn't go without power. Okay. So, but I mean, this thing is unbelievable, right? 200,000 miles of high voltage transmission lines, but it's the 5.5 million miles of local distribution lines that sit within the cities that get electricity into every wall in America. This was ranked the greatest achievement of the 20th century by the National Academy of Engineering. It's unreal. Like, this is it. Okay. So let's talk about just a general overview of the power grid. You can tell that this is a career, right? There are many careers. There are so many different ways to work in this industry, building, generation plant, building transformers, building transmission lines, designing substations, all these things that you probably have never heard about. But it's a massive field in itself. So you can become a power engineer, and it's fun. But there's really four kind of components to the power grid. So the first is generation. So this is electric generators somewhere spinning. Okay, so as long as we can spin, we can get electricity. And most of these, we look at this, almost all of them, the vast majority, is boiling water to create steam to spin a turbine that spins an electric generator. And those things, we can use thermal, we can use coal, we can use natural gas, but it just spins those electrical generators. Then what we do, though, is we step up. Now this is AC, okay, always AC. We step up the voltage at the plant, and then we do what we call transmission. And transmission is the long haul. So that's the stuff you see driving down the interstate. And you'll see why in a second as we talk about this. But this is transmitting electricity at very high voltages. So this is like, 230 kilovolts, 138 kilovolts, 345 kilovolts, 500 kilovolts or kV. And of course, if I didn't specify what unit we're talking about here with voltage, this is RMS, right? And then what happens is as you get closer to cities, you want to step it down because the high voltages are a little bit dangerous. That's why they're, spread apart and they're kind of off away from people. So what we do is we step it down when we get closer to cities, and that's called a substation. I'll show you a picture of that in a second. And then what happens is you have a lower voltage that is then distributed across the city. And there's some customers, industrial plants that'll be able to tie into kind of that step down voltage. And this is in like the, 13 kV, 4 kV, those type of numbers. And then there's us. Okay, so we're the households, and they step it down one last time to get it down into the voltage levels that we see in our walls, which is 120 volts or 240 volts for kind of our dryers. And so this is kind of the whole thing. Transmission is the long haul, distribution is throughout the cities, and then the end user is kind of us. All right. So Here are some pictures of what transmission looks like versus what distribution looks like. So transmission are these massive poles that you see down the interstate, and you don't see a lot of them, I mean, you do see a lot of them, but a lot of these are hidden because they go through forests that you don't even see. But distribution is this type of stuff. So you've probably seen these power poles that sit in a city, these wooden poles, and they try to bury them now, but these are still everywhere. And you notice these little cans on here? This is the final transformer that actually steps it down before it runs to your house. So this is kind of what distribution looks like. Transformers all the way. So if you think about what these transformers are, when you step it down, this substation right here, the last step coming off the transmission line before it gets distributed throughout the city, you've probably seen these driving around. These are substations. So they try to make them look nice now. They'll build like a brick wall around it, but you see these everywhere. They're just like this group of random machines that's just in the middle of a city, and they're all over the city. You're like, what is this stuff? It's like, that's what it is. It's a substation. These are transformers that step down the high voltages in order to get them to a point where you can do distribution. And then finally on distribution, kind of the last transformer before you see it go into the house, you probably have seen these before. These cans that are sit on these poles, these are transformers. And it's just like, these are the most popular type of transformers. You can also have the ones that are like sit on a pad. They look kind of like a little box that sits in your yard on a concrete pad. But these transformers are what you see the most often. And in reality, when you have like storms, these are the things that blow up, because these transformers, in order to make them, more efficient, they kind of soak them in these oils to make, or they have oil in them, or a material that is flammable, I guess. That allows the magnetic fields to couple stronger between the primary and secondary windings. And so these are the ones, when you look at storms and you see all these explosions on the side of a street, that's what's blowing up. It's the transformers. Okay, so you got to be asking yourself, why is the power grid AC? And this goes back in history to one of the kind of greatest battles of intellectuals that has happened in our recent times. And this was we called it the current war. And this was Nikola Tesla versus Thomas Edison. So as you can imagine, all these scientific breakthroughs were happening with electricity in the 1800s, late 1700s and 1800s. And you can imagine that there was this rush to say, hey, how can we make money off of this? And so the electrical grid started as this kind of business venture where people said, I want to give people electricity. Okay. And so we need people who are going to generate electricity. We need utility companies that will distribute the electricity. And then if we can get electricity into people's homes, we can sell them devices that run off electricity. So appliances and light bulbs and toasters. And this was just like going to be this huge economic boon to the country. And it absolutely ended up being that way. And so when it all first started, this is like in the late 1800s, Thomas Edison was an inventor. You probably heard of him. So he had tons and tons of patents. And he was one of the first to try to go after creating a generation company that would provide electricity to users. And so the first plant was this Pearl Street Station in Manhattan, New York in 1882. And he started this company called the Edison Electric Company, or the Edison Electric Illuminating Company. A lot of times people just say Edison Electric. But so he creates this company, and it was based on generating DC power. Okay. And so DC was, that's how he decided that it would work. Okay, so you'd get some constant DC voltage in your home, and life is good. One of the issues, though, with it was that there was a desire to kind of step up and step down the voltages, and you'll see why in a minute. But basically, if you could conserve power and you could somehow step up the voltage and reduce the current and achieve the same power, you could reduce loss in the transmission due to the resistance of the cables. And so this was kind of everybody understood this, but it was really difficult to do at the time on DC power. So there was an alternative to this that Nikola Tesla came up with, and this was the AC power. And so the reason that AC power worked better was because you could use transformers in order to step up and step down the voltage. So we've already covered what a transformer is. It's basically coils of wires that are magnetically coupled to each other, but it only works on AC signals. And And so there was a company called Westinghouse Electric Corporation, and this was George Westinghouse was the guy that founded this. And he had demonstrated some of these in Europe of like an AC power grid, and using this concept of a transformer to step up and step down the voltages. And so there was this big battle of like who was going to win, who was going to be the primary producer of the power grid, because you probably couldn't have both, right? I mean, it would be better to either stick with AC or stick with DC. And so, of course, this is what was kind of interesting about this, is that Tesla was like this genius, Thomas Edison was this genius, and they had these two competing ideas on how to do it. And Edison was first, right? So he was making royalties off of his patents on this DC power distribution, and he had this company and everything. And so what was funny about it is as Westinghouse started using Tesla's ideas and started licensing Tesla's patents, Edison didn't want that to happen, and Edison actually started this campaign against AC current and AC power, and it was like this real kind of interesting thing to watch, you know, from now looking back in history. But there was like this slur campaign against AC power, that it wasn't safe and all this sort of stuff. And so they called this the current war, and there's a whole bunch of movies and books about this, but it was really this fascinating thing. And it all kind of came to a head in 1893. So this is where they say the current war kind of ended. And it was there was this thing called the World's Fair, and it was going to be held in Chicago. And one of the things that they wanted to do was they wanted to light up the World Fair with electricity. Now, at the time, that nobody had like light bulbs and lights, you know, street lights all over the place. So it was like this huge thing if you could actually have buildings that had lights and street lamps all over the place. And they wanted to show this huge exposition. They wanted to like shut down the fair by saying, look at the future. We're going to light it up with electricity, and have all these light bulbs. So the two companies bid on it, right? And General Electric was another company that was forming that was going to be like a power producer. And they said, we think that we're going to go with Edison. So we like the DC approach, and they bid on the fair. Well, then Westinghouse also bid on the fair using the AC approach. And it was really fascinating because here it was, where it was kind of like this first major, you know, customer, but also this huge demonstration that was going to show the world what the future was. And they had to pick whether it was going to be AC or DC. And it turned out that the fair chose AC. They came in with a lower bid, and the World Fair was lit up with AC power. And then what happened, well, kind of the final nail in the coffin was later that year, a company called Niagara Falls Power Company, they decided to start this venture where they were going to actually use the hydroelectric capability of Niagara Falls and power Buffalo, New York. And this was like this first like really large scale initiative to say, I'm gonna power a whole city using hydroelectric power. And they decided to use AC power. And that then tipped the scales, because General Electric then said, you know what, I think it's going AC. And General Electric basically jumped ship and started adopting the AC model. And that kind of left the whole DC and the Edison Electric Company, and they merged and went bankrupt and all sorts of stuff. And there's still remnants of it today. But basically this was kind of the end of what we call the current war. And that then started building the grid using AC. Okay. And so if you answer the question now, it's like, what was the real answer? Well, it's because we can use transformers to step up and step down voltages and currents easily, because transformers were easy to make. And so if you use DC power, it was more difficult to step up and step down back then. Now, if you fast forward to today, we do have some DC in our power grid. So technology has advanced, and there are ways to step up and step down DC voltages and currents. And if you look at this power grid, you'll notice that there's some high voltage direct current lines that exist. So there's a really, really long one that goes from like Oregon down to California. And then there's another one here that goes kind of from, you know, in Utah down into Nevada. And then there's some stuff over here that does, you know, North Dakota into Minnesota. And so DC does play a part within our AC power grid, but it's currently kind of a small fraction when you just look at the map. Okay, so let's do an example of why it's important to step up and step down AC power. So let's look at this example right here. So let's say you have a power plant and it's going to generate electricity. And then you have a home, which is going to use electricity. And so this is generation, and this is going to be your end user. And you're going to transmit it. Okay, so you're going to use transmission lines to do this long haul. And we're going to simplify this problem really quick, so we won't talk about distribution or anything like that. So let's look at an example where you don't step up the voltage and step down the current as you transmit it. So now when you think about something like this, here's kind of how sources and loads work. If you remember, the load will take whatever it takes, right? So it's going to try to pull however much current it needs to power all the devices that are on in the home. And then what the plant does is the generation will create or source that electricity or that power as much as the load needs up to its capacity. So basically, if the home is pulling 1 watt, then the power plant will generate 1 watt. And if it's pulling 1260, then it's going to pull 1260. Okay, so it turns out that an average home in America consumes about 1260 watts. Now remember that's watts as a rate, right? So that's joules per second. And so in a home we're like at 120 volts AC, 10.5 amps AC, and that's all RMS, but that's kind of about the amount of power that we're consuming continuously over time. And so let's take a look at what happens when you try to pull that current. Let's just say we're going to deliver that 10.5 amps through a transmission line that has resistive loss. Okay, so here's an example of transmission line loss. Cable loss for transmission lines tends to be somewhere in the order of 22 microohms per meter. And let's just do an example where you're relatively close to the power plant. You're like 62 miles away, let's say, which comes out to be 100,000 meters. So it's a nice, nice round number here. So let's go ahead and calculate what our total resistance would be in the transmission line, and then we'll look at how much loss we have due to that 10.5 amps going through those resistors. Okay, so the resistance is found pretty easily by just multiplying. So 22 microohms per meter, so that's a specification of the cable, multiplied by 100,000 meters. Okay, and so when we go to calculate that, okay, so bring out a buddy over here, and we got 22 exponent 6 negative times 100,000, and we end up being 2.2 ohms. Okay, so not a ton, right? So it's not like a huge amount of resistance, but it is something. Okay, so now here's the question: what power is lost in the transmission? And we're going to use P is equal to I squared R in order to calculate that, because we have a resistance and we're trying to pull current through it. And so if I come along, I've got 10.5 amps squared multiplied by 2.2 ohms, okay? And what I end up with there is this. So if I come along, let me turn this off so you can see that a little clearer. I'm gonna come along and I'm gonna say 10.5 squared times 2.2. And so what happens is I end up having 242.5 watts lost in the transmission. Okay, so that is actually just power that's lost in the cables. All right, and so the way that it works though is if you think about the source, okay, it is going to provide whatever the loss is in the cable plus the load. Okay, and so some people call the loss part of the load, but it really is, like, if you look at this, I have 242.5, okay, plus our home loss, or our home load, which is 1260, okay, and you add those together, what you end up with is 1260, and you get 1502 watts. Well, that 1500 watts is provided by the source. So you think about that, it's going to provide that because that's what's being pulled by the load and the loss, or you could lump all this together as a load. And as long as it's up, not exceeding its capacity. And so you're looking at that and it's like, well, is that really bad? Well, let's take a look at how much power we actually just threw away in heat in the cables. Well, so I can take 242.5 divided by 1502 and multiply by 100 to figure out the percentage that 242 is of that number. So if I come along here, I can say 242.5 divided by 1502 and then times 100, and I'm left with 16%. That is a lot of power to just throw away. Okay, so we have this very expensive generation plant, and we are just going to throw 16% of it away for no reason. okay? Just because we don't want to use transformers. Okay, so now let's look at an example of we're gonna now use a transformer and step up and step down the voltages and currents, okay? So in this example, what is really the most important is stepping up or stepping down the current. So for example, let's go back in here. We still have the same cable, okay? So we still have 2.2 ohms right here, and the home still pulls 1260 watts, okay? And so what happens though is we are gonna step up the voltage and in turn step down the current by a factor of 2,000, okay? So this is your turn factor. And then what we'll do is we'll step down once we get to the end. And so what really is going to happen is what we are going to do is, if you remember, once I step up, so let's remember our transformer here. So you've got a transformer and what we're going to do is we have this N of 2000, right? And we have I1 and you have I2. And so if you remember, once you step up the voltage, you step down the current. So it's going to be I1 divided by N, so which is I1 divided by 2,000, okay? And so if you think about that, now we can use that to calculate how much current is actually going to flow through the wire once we go through the first transformer that steps the voltage way, way up and the current way, way down. So the current that we started with was 10.5, and now we're going to divide that by 2,000, and now we have this very small current. So let's take a look at what that is. So 10.5, and we're going to divide it by 2,000. And so we end up with this 5.25 milliamps. So now you sit there and you go, well, this is kind of nuts. You were able to take the current and go way, way down before you transmitted it. And the answer is yes, we were, because we took the power and went way, way up. And remember, that's how a transformer works, is the power in is equal to the power out in an ideal transformer with no loss. And then what we can do is once we get down to the other side, we can step it down with the same turn ratio and we get the exact same power back. The reason we did that was we preserved power throughout the whole transmission, but we were able to get the current to go way, way down. So now let's go look at this calculation now of what this current is in terms of loss. So we have power is equal to I squared R. This is the loss in that cable. And now I've got 5.25 milliamps times the original 2.2 ohms. And now I can take this and I can say, okay, there's my current now, and I can square it times 2.2. And now I'm left with, holy moly, it's like 0.06 microwatts. Is that right? 0.06 exponent 6 negative. No, it's like 60 it's like 60 microwatts. So if I do 60 exponent 6 negative 60 microwatts, I get 60 microwatts. Okay, let's do that calculation again. So 5.25 exponent 3 negative squared times 2.2 is equal to 6 times 10 to the negative 5. So if I entered 60 exponent 6 negative, it's 6 times the negative 5. So I only have 60 microwatts. Now let's compare that to our original percentage. So now how much power is actually getting lost? Well, you can almost say it's 0, because if I came down here and did this, I'd be like 60 microwatts over 1260 plus 60 microwatts. That is the how much of a percentage of 60 micro is it to the total amount that this generator had to actually send down. And so what I'd have here is I'll take this 60 microwatts and I'll add it to, actually let's do this. Let's actually do it. So 60, 6 negative, okay. And then I'm gonna go divided by, open parentheses, I'm gonna go 1260 plus 60 exponent 6 negative, close parentheses, equal, and then times 100, and that is my percentage. And it's not even, you can't even see it, okay? It's like almost 0, okay? So you're measuring it in micro percentages. And then that means that the source only had to provide essentially the power used by the home, okay? So this is really it. This is what it's all about. That's why AC took over. It's because of the loss in cables. You can't have a perfect cable. It's always gonna have some loss. And even though it is a small amount of loss, and it's only a couple ohms for something that's even 62 miles long, once you start taking that current and squaring it and multiplying by the resistance, it becomes a significant number. And imagine now if you're putting down, kiloamps through this thing. I mean, you get it to a point where it goes fast. Okay, so that is a high level overview of the electrical power grid, why we use AC signals, and why the transformer is so key to it. All right, see ya.